Delaware Tech, Chemistry 100, Chemistry 110, pH indicators. pH indicators, or indicator dyes, are molecules that change color at different pH levels. So they may be one color at a lower pH and another color at a higher pH. We also have pH indicators that change fluorescence. They may go from no fluorescence to fluorescence, or fluorescence to no fluorescence, or even one kind of fluorescence in one color range to another kind of fluorescence in another color range, depending on the pH. And here's just a table of just a handful of the literally hundreds of different indicator dyes that are available out there. We're going to strictly keep it to color change indicators, or indicator dyes. And so here are a list of a little more than a dozen indicators, and you see that each one of these has a different pH range where the color occurs. So let's just look at one of them. Let's just look at methyl purple, and I'll just circle that for a second here, right here, methyl purple. And what this is telling us is that below pH 4.8 it's purple, and above pH 5.4 it's green, and between those two pHs it's something between green and purple, whatever color that is. And you'll see this for each of these, and shown here is what we call a microtiter plate. This is a plastic plate with 96 individual wells in it, little spaces where you could put chemicals into 96 different boxes and do 96 different reactions. And in this particular plate, like most of the 96 well plates are all arranged in 12 rows, 12 columns by 8 rows. So they're 8 by 12 boxes on here, a total of 96 wells. And you'll notice in this particular plate, what's happened is every column has a different pH solution that was placed in it. So the first column has a pH 1 solution, the second column is a pH 2, etc., all the way to the last column, which is a pH 12 solution. And every row has a different dye in it. So let's just take a look at one of these dyes. Let's look at the last one, thymol blue. And if we look on our chart here, thymol blue actually appears twice. This is an unusual one. It appears twice. So we see that at very low pH range, there's a transition from red to yellow, and then at higher pHs, there's a transition from yellow to blue. So if we were to look at just the chart here, this would say, if we had a pH range, and I'm just going to put a number of pHs in here. If we had a pH range, this says that below 1.2, so if this was 1.2, it would be red. And above 2.8, let's say this is 2.8, this is not to scale obviously, we would expect yellow. And in between, we might expect something between red and yellow. Who knows what that might be? Maybe orange. We'll put a little orange, put a little note here, orange. Let me write that again. It's a little sloppy. And we'll put a little note that maybe it's orange in between 1.2 and 2.8. And then you'll notice below 8.0 we expect yellow. Well, that's what we've got. Below 8.0 it is yellow. And by the time we're at 9.6, we might expect the color to change to blue. And maybe the in-between color between 8.0 and 9.6 might be green. We don't know. Sometimes it is, sometimes it's not. Sometimes you have to be right in the exact right pH to get that intermediate color. But take a look at what we have. We have pink down at the bottom, not quite red, but maybe we don't have enough dye in there to make it look fully red. And at the end, we have clearly blue at the end, above pH 6. So here's 10, 11, and 12, all at a blue color. And then we expect there to be a transition somewhere between 1.2 and 2.8. Well, it doesn't look like that transition is particularly in the orange range. It looks more like pinkish. And then there is a little bit of orange by the time you get to 4, which is not exactly what the chart tells us. And then we clearly have yellow in the middle. And then it's yellow until 8. and you can see that matches perfectly. And then there's a transition to blue, and it looks like our intermediate colors aren't what we expect, but sometimes they are, sometimes they aren't. But the in-between colors are clearly matching. Red is pinkish, that's close enough. Yellow is yellow, and blue is blue. And this is the kind of pattern we would see. And I'm going to erase this because this is a very sloppy representation here, but this is the type of pattern you'll see. In reality, it's a little more complicated, but we're going to assume this chart is correct for now. So let's look at a couple examples. Well, what makes indicator dyes indicators, in other words, color changers, is that they have two forms. There's the form when the indicator dye has a proton on it, and that's called the acidic form or the acid form of the dye. And there's a form when the indicator doesn't have that proton on it. So I've represented it as indicator with a negative sign. I could have written this, by the way, as indicator with an H plus here to show a proton, and I could have written this as an indicator with no charge here and maybe a lone pair of electrons. It doesn't matter which way you write it. It's still, this is the basic form and this is the acidic form. And it turns out because one has a proton on it and one doesn't, they actually have different structures, slightly different, but it's enough to cause the color of the molecule to change dramatically. And that will happen at different pHs for every molecule that we're doing it. And that's why we have these ranges if we go back. That's why every one of these molecules has a different range when it switches color. So let's look at a couple problems that involve pH indicators. So we used to use these a lot more when labs have a lot of money and can afford to buy good pH meters that will tell us just what our pH is to 2 decimal places or even 3 decimal places. We don't need pH indicators, but if you're trying to do a lot of experiments and trying to keep it cheap and quick, and maybe you don't have the volume to stick a pH meter in, indicators are very, very useful. So here's a problem. Bromothymol blue is actually blue. Phenolphthalein is colorless. Well, how do we know what anything means? We need to have our chart. So here's our chart. So first we look at bromothymol blue. We find it on our chart, and there it is right here. And we find phenolphthalein, that's right here. And phenolphthalein is a very old, very common indicator dye. It's been used for years and years. It's still used, very popular with chemists and even with young students doing science projects. Now you'll notice bromothymol blue changes from yellow when it's lower than pH 6, and it changes to blue when it's higher than pH 7.6, and it's somewhere in the middle. Whereas phenolphthalein is colorless. I'll write colorless, CL for colorless, when it's below 8.2, and it's pink when it's above pH 10. And that's how you make this assessment. But what we see is that the bromothymol blue is in fact blue, so we know it's higher than 7.6. And we see the phenolphthalein is colorless, so we know it's less than or equal to 8.2. Well, if it's greater than 7.6 and it's less than 8.2, then our pH must be somewhere between 7.6 and 8.2, and that's how we figure out where our pH is. It's not a perfect answer of our pH, but it gives us a close idea that our pH is somewhere around pH 8, give or take a few tenths of a pH unit. Here's another problem. Methyl orange is yellow, and ethyl red is pink. Well, let's find methyl orange. Methyl orange is way up here, and ethyl red is just below it. And we see that methyl orange is yellow, and ethyl red is pink. Well, there is no pink. I see colorless and red. So pink tells us it's right in the middle between these two pHs, and the yellow tells us it's above pH 4. So we have methyl orange telling us that the pH is greater than or equal to 4.4, and we have a pink ethyl red in the middle telling us it's somewhere in that transition of 4.0 to 5.8. Well, if it's greater than 4.4, but it has to be between 4.0 and 5.8, well, then we know the pH must be between 4.4 and 5.8. And we can't really narrow it down unless we use other pH indicators that we might get. Maybe nothing on this chart, but we might have something somewhere else that also changes color. But you're going to look for things that all change within this range. So I would look for numbers in here, like any of these values might be useful to us. And we see what colors each of these is. And that may allow us to narrow our range down a little bit more. So we might use 3 dyes or even 4. Here's another problem. Alizarin yellow R is yellow, and thymolphthalein, and that's how we pronounce it, phthalate, kind of a PH-TH sound. You say the PH super quick. It's mostly the TH, so it's thymolphthalein, is pale blue. Well, alizarin yellow R goes from yellow to red, and we're told it's yellow, so we know it's less than pH 10.1. And we also know that thymolphthalein, which is listed right above it, is pale blue. Well, we're told our transition happens from colorless to blue. Well, pale blue would be right in between colorless and pale blue. So that tells us it's in the middle of these numbers, between 9.4 and 10.6. Well, if we know it's less than 10.1, and we know it's between 9.4 and 10.6, well, that leaves us the range that it's between 9.4 and 10.1. And this is how you use pH indicators to at least narrow down the range of your pH when you don't have a pH meter available.